Hello students, in previous lecture we have talked about the subspace of metric space. We have proved results about the subspaces. Today we'll see one more result on subspace and then we'll study concept of product metric space. So take the theorem on subspace. Let XD be a metric space or let YD be subspace of metric space XD, subspace of metric space XD and A is a subset of Y and A is subset of Y. Then first part, X belongs to Y is the limit point or cluster point. Cluster point of A, cluster which is also known as limit point. Okay. If and only if it is a limit point, if and only if X is limit point of or cluster point of A in X. B part, the closure of A in Y is the closure of A in Y is a closure intersection X, where a closure is closure of A in X. So we'll prove these two results one by one. What is the definition of cluster point? So X is said to be cluster point of A if every open sphere about X contains some point of A other than X, and it is cluster point of A in Y if every open sphere about X in Y contain at least one point of A. Okay. So here for any r greater than 0, if I take the open sphere about X in X minus X intersection A set, this must be equal to SRX X minus X intersection A intersection Y, since A is subset of Y. So A is equal to A intersection Y. Okay. So I can write this as SRX X intersection Y minus X intersection E. Okay. And this is precisely SRY X minus X intersection E. We'll give 1 for this. Okay. Now X belongs to X is cluster point of A in X if and only for any r greater than 0, if and only for any r greater than 0 open sphere about x minus x, intersection A, this must be non-empty. If and only for every r greater than 0, SRY, x minus x intersection A must be non-empty. From 1, what this implies is if and only x is cluster point of A in Y, A in Y. Is it clear? So only from 1 we are getting if and only condition. Only from 1 we are getting if and only condition. B part, what we have to show? The closure of A in Y is precisely a closure intersection Y. Okay, to show closure of A in Y is a closure intersection Y or a closure X. We'll take a closure X intersection Y, where a closure X is closure of X, closure of A in X. Okay. Let a closure Y is equal to closure of A in Y. A in Y. So by definition of closure, AX closure is set of X belongs to X such that every open sphere about X in X intersection A must be non-empty for every r greater than 0, and a closure Y is equal to set of X belongs to Y such that SRX SRY intersection A, this must be non-empty for every r greater than 0. For every r greater than 0. But now as A is subset of Y, okay, as A is subset of Y, what is our claim? A closure X is equal to a closure Y. This is our aim. This is your AX intersection Y. This is our aim. Is it clear? So for this, for any r greater than 0, now for any r greater than 0, any r greater than 0, if I take SRX, X intersection A, then this is same as SRXX intersection A intersection Y, since A is subset of Y, implies A intersection Y is equal to A, and that's why this is equal to SRX intersection Y intersection A again, but this is precisely SRY intersection A for any A. Okay. This is now say 1. This is say 1. So from this x belongs to x lies in ax closure or ay closure if and only for any r greater than 0 s or y, sorry, here x remains intersection s or y x intersection a is non-empty if and only for every r greater than 0 s or x intersection a is non-empty set. If and only x belongs to ax closure, is it right? So if x lies in ay closure, then it also lies here, and conversely if it is in x closure, then it is there. Okay. So this implies what is my ay closure? This ay closure is precisely ax closure intersection y. This is 1, this is 2. Okay. This is 2. So x belongs to ax closure. But ay closure is nothing but x closure intersection, and therefore ay closure is equal to ax closure intersection y. Is it clear? Therefore ay closure is equal to ax closure intersection y. Thus result is proved. Now we'll study concept of product of metric spaces. So on Rn, on R2, say, we have taken matrix on R2 for x bar is equal to x1, x2 and y bar is equal to y1, y2 belongs to R2. d1 of x bar, y bar is defined as mod of x1 minus y1 plus mod of x2 minus y2. d2 of x bar, y bar is defined as summation of our x1 minus y1 its square plus x2 minus y2 bracket square raised to half. And d infinity of x bar, y bar is defined as maximum of mod of x1 minus y1 x2 minus y2. But what is this R2 set? It is nothing but R cross R. So for that R, I am taking matrix from Ru. For this R, it is also usual matrix from Ru. we'll extend this idea to define product matrix space. Okay, so that xd1 and yd2 be matrix spaces. Then x cross y set, order set, is set of xy where x values in x, y values in y. Y values in y. Then for p is equal to, say, if I take say x1 d1 and here we'll take x2 d2, then we'll get x1 cross x2 set is x1 x2 where x1 belongs to x1 and x2 belongs to x2. I'll take this notation. Then for x bar is equal to x1 x2 comma y bar is equal to y1 y2 in x cross y. If I take d1 of x bar y bar is equal to d1 of x bar y bar is equal to d1 of say I'll take the notation, say d star here, d star is equal to d1 of first component x1 y1 plus d2 of x2 y2. Okay, x1 y1 are members of x1, x2 y2 are members of x2. So d2 of x2 y2 is well defined, d1 of x1 y1 is well defined. Okay, if I take this, if I take d double star of x bar y bar to be, say, d1 of x1 y1 its square plus d2 of x2 y2 its square under root of that, this metric. And if I take d infinity of x bar y bar is equal to maximum of d1 of x1 y1 d2 of x2 y2. If I take functions defined on x1 cross x2 by x1 cross x2. Okay, these are functions from actually, these are functions from x1 cross x2 cross x1 cross x2 to R. Remember it. Okay. If I take this as y set, right? Means it is function, D is a matrix from y cross y to R. Y cross y to R. Is it clear? So, then D star, D double star, D infinity are matrix for x1 cross x2. Moreover, they are equivalent matrix. Moreover, they are equivalent matrix. So what were done for R2? While showing D1, D2, D infinity are matrix and they are equivalent on parallel line, you can easily show that these functions defines matrix and they are equivalent matrix. They are equivalent matrix. I can extend this also extension if xi di I equal to 1 2 dot dot up to n are metric spaces, and y is equal to say x1 cross x2 cross dot dot up to xn. Then for x bar is equal to x1 x2 dot dot up to xn, y bar is equal to y1 dot dot up to yn belongs to y. x1 cross x2 cross xn, if I take again on same line, say d star of x bar y bar is equal to summation of mod of summation of di xi yi I equal to 1 to n. If I take d double star x bar y bar as summation of di xi yi its square raised to half I equal to 1 to n, and d infinity of x bar y bar to be d infinity of x bar y bar to be maximum of di xi yi 1 less equal I less equal n. Then d star d double star d infinity are matrix for y is equal to x1 cross x2 cross dot dot up to xn, and they are equivalent matrix. They are equivalent matrix. In fact, if I have some G1 is open subset of x1, G2 is open subset of x2 dot dot up to Gn is open subset of xn, then the Cartesian product set G1 cross G2 cross dot dot up to Gn is also open set in Y with respect to any one of these metric. Same story is there for closed sets. Same story is there for closed sets. So in this way, product matrix space define, and that such type of function gives rise to metric defined on that matrix. So we are defining metric on product Cartesian product of matrix spaces by using the metric defined on Rn or R2. Rn or R2. So to prove these are matrices is not difficult. How we have proved that that d1, d2, d infinity defined on Rn are equivalent matrix on same line. You can easily show that these are equivalent matrix. So solve these examples on your own for your practice. So then it will be very helpful for clearing the concept of matrix spaces. So with this discussion today, I like to stop here, and hereby our first topic, introductory concepts in matrix spaces, is over. Later on, we have to study concept of complete matrix spaces, compact matrix spaces, continuous function defined from one matrix space to other matrix spaces. So till that, bye bye. I request all of you go through all sessions. If you like session, then like the sessions and also subscribe channel to get the free online videos on matrix spaces real analysis courses. Thank you.